Hello, Rustaceans. This is Haoran from University of Washington, and today I'm super excited to bring to you my work, Hayroll, a modular wrapper for translating C macros and conditional compilation to Rust. Hayroll itself is an acronym for Harvest Annotator for Using Regions of Lexical Logic, while Harvest is our UW Harvest team, is our C to Rust translation team at UW. Yeah, why translate C to Rust? Skipped, thanks to CPP to Rust and Raffinator. Now, why translate C macros to Rust? Existing transpilers, for example, C to Rust, state-of-the-art, lose macros and configurability during translation. It takes in unpreprocessed C, which have macro names, and configurable compiler flags. But after it's translated to Rust, you get the Rust that lose macro names and have only fixed compiler flags. This information loss that's happening during the process is due to them running the C preprocessor in advance. They didn't do anything bad, they just ran the C preprocessor, which erased all this information. Well, we don't really want that. And an example of, we decided that macros in conditional compilation is such an integral part of C. People use them to write everything from constant to like small implementations of min, max, all kinds of that things. We decided to implement Hayroll. Hayroll translates C macros into Rust functions or macros, and it also translates C conditional compilation into Rust CFG blocks. Hayroll is the first and, as of now, the only system that handles the problem. Here's an example of pre-preprocessed C and post-preprocessed C. So here we have a conditional range here and a statement macro together with an expression macro. It is not clear that like the mapping relationship between each other until I highlight it for you. And a result of taking that pre-processed C as an input before your C to Rust translation is that you get the same problem on the Rust side. It's not clear which part corresponds to which part. If you want to rebuild them into macros, you first have to know which macros they're from. It's not clear until I highlight it for you. So that raises our first challenge, which is the source correspondence challenge. That is not yet the end of the story because we are still missing this conditional compilation range. The ifdev libmcs fpudez flag is entirely lost because during this run of the C to Rust, we didn't define this flag here. They didn't pass it to the preprocessor, so that's lost. Reasonable. But if you run C to Rust again with that, you can see it producing an entirely different software version with this line of code hard-coded into it. Imagine we have like 10 such flags. We're ending up getting like 1,024 different versions of the software, which is not what we really want. What we want, this raises the second challenge, which is this configuration explosion problem. What we really want here is just one version of software that is configurable and have all macros and conditional compilation rebuilt into the Rust native way. If we dive deeper into this problem, we will then realize why C to Rust decided to run the preprocessor. The root cause is that C preprocessor is a different language from C itself. This is a typical C compilation pipeline where you start with C macros, which are just strings, no more than strings. You run C preprocessor, it's going to get you the pure C string. And then the C parser is going to parse it into CAST. All of those transpilers work on the CAST because they are AST rewrites. But macros are defined all the way back here. They're just strings. This raises our third challenge, which is analyzing these bunch of strings requires an entirely different technique than analyzing an AST. This also raises a practical engineering challenge, which is if we want all these existing C to Rust translators, C to Rust, C++ to Rust, which we've just seen, and maybe my C to Rust in the future, who knows. If we want them to all support macro, they have to also dump a bunch of logic that's unrelated to their AST handling into their pipeline. Very tedious. We don't want everybody to do this, so we decided to isolate this problem, building Hayroll as a wrapper around any macro-oblivious translator to make them macro-aware. Summarization of our challenges and our solutions. To isolate this problem, we built Hayroll as a wrapper. To do macro analysis, we made use of Mackie, an existing macro analyzer tool. To handle the configuration explosion problem, we wrote a symbolic executor, not for C, but just for C preprocessor. And for source correspondence problem, we developed an in-AST tagging technique, which we call seeding. These solutions either become a component in our pipeline or become a pipeline design itself. Hayroll architecture. Hayroll is divided into 3 layers: the conditional compilation translation layer, the macro translation layer, and transpiler layer. Each layer handles one of these important challenges and then passes the task down to an underlying layer for another different challenge. Let's start from the conditional compilation translation layer. We first send the C code through Pioneer symbolic executor, which tells you for each line of the code what is the enabling condition. That is, the configuration flags combinations that's required to enable this line of code. Then that information is sent through the splitter, which splits one configurable software into many configuration-specific softwares that together cover each line of the original functionality. Then each one of these copies are then sent through the macro translation layer, where it first meets the Mackie macro analyzer. It tells us useful properties of macros. For example, are they statements or expressions? Are they syntactical? Are they hygienic? And with that information, we then send the C code with that information into Seeder, where it puts in-AST tags, which we call seeds, into the original C code. And that part is then sent through the underlying transpiler Seeder Rust here. They translate not only the C code, but also the seeds all together onto the Rust side. Then our Reaper will be able to recognize all these seeds, then rebuild macros into the Rust translation. That is then sent back to the conditional compilation translation layer, where the merger merges all copies of the softwares into one copy of configurable software. We will start layer by layer, starting from the Pioneer symbolic executor. So, motivation. Why do we even need symbolic execution for for analyzing C macros? C conditional compilation. Here's an example. Just by looking at this code snippet, can you answer me, to enable this conditional compilation, shall we just define this __ libmcf's fu-des flag? Is that all we need? You will not be able to answer this question because I didn't show you all of that. But if you actually tried that, you will see GCC compile with this flag. It's going to tell you error undefined reference to this variable. Yeah, what is happening? What you really need to do is look at all the header file it includes. That's where you find you're not supposed to use this flag as a user, and you're supposed to use non-underscored version of the flag, which sets up this flag for you, and also a lot of other variables. This is to say that C conditional compilation requires global reasoning, because they could have nested flags or derive flags or even arithmetic computations between flags, comparisons between flags, all requiring a symbolic executor to find out. With our symbolic executor, you will know that both of these conditional ranges are enabled by the same flag, which is not the internal flag. After that, we send that information into the splitter, which is in charge of splitting a configurable program into many configuration-specific programs that together cover every line of code. For example, for the code snippet on the left, how many different configuration combinations are needed to cover every possibility? There are 3 flags, and 2 to the power of 3 is 8. So you can totally do 8. Well, that's sound, but not very efficient, because remember, each of these combinations means a run of the entire underlying macro translation layer. We don't want it to happen, so we instead used a greedy algorithm, which is to try to satisfy the most deeply nested line first. So we issue a combination which is defined feature 1 and 2, which will cover line 1 through 4, and we'll be able to realize that it also happens to cover 2 more lines with no extra configuration needed. And by repeating this process, we'll be able to cover all the configurations with just 3 different combinations, which is much more efficient. Then later, we're going into the macro translation layer. We're first going to introduce the Mackie macro analysis. Why do we need to analyze these macros? What do we need to know about these macros? This sourced from the problem of a macro translatability problem. Hayroll doesn't translate all macros. There are some macros with really bad properties that we have to keep expanded. For example, well, C macros are really just string copy-paste, and you can do really crazy things with them. You cannot translate all of them to Rust. For example, you can define semicolon to a semicolon and use that to close every expression. Totally legal, entirely insane. We are not going to translate that. A lot of other examples are here, but these are the ones that we'll just leave expanded. They're not going to prevent the program from translating it. We're just falling back to what cd-rust does. And a category that has slightly better properties, but also steps onto one of these properties, they can be translated into Rust macros, but not Rust functions yet. The ones with the best properties, essentially function no macros, they can be translated into Rust functions. And how do we know these properties? We made use of Mackie, and also we modified it a little bit. It was able to capture these properties by implementing a hook in Client C preprocessor, essentially align them to AST nodes that have these properties, if they align with AST nodes at all. Okay, then we're going into the Cedar Reaper part of our program, which is for solving the source correspondence problem. Remember, the ultimate goal of source correspondence problem solving is to know which part of the Rust code was from which C macro expansion or C conditional compilation range. We did it in a non-intuitive way. First, the Cedar is going to put in-code AST tags into the C code before the cd-rust translation. These tags are syntactically preserving. For example, here, a statement after seeding are still statements. They're semantically preserving because these extra statements are no ops. They do not do anything, and it can carry metadata. After the benefit of having these properties is that after cd-rust translation, you keep this kind of sandwich structure of seeds and its contents. So whatever this macro is translated into, expanded, some unreadable range of things, it doesn't matter. It's still sandwiched by these two statements over here. So our Reaper will be able to pick up these tags and wrap them back into Rust, either macros or functions. That's Cedar plus Reaper. So for different kinds of AST nodes, the seeding technique is a little bit different. We just introduced seeding statements, which is quite easy, just sandwich the structure. For seeding expressions, it's a little bit more tricky, but we managed to do it. Remember these properties. We want them to be syntactically preserving. We want the entire thing to still be an expression. And we want it to be semantically preserving. We want them to be evaluated to the same value. And we want them to be able to carry metadata. So we end up using this conditional expression. Some people also call them ternary expression in C, where we put the string, the metadata, into the condition clause, which should always evaluate to a non-zero value, meaning it should always take this, the first branch. Second branch, we are just satisfying the compiler with something of the correct type that you shouldn't really go to. You should never be able to reach that. And after that's being translated by cd-rust, you get this if expression in Rust, something, you all know it, something very easy to pick up and recognize by the Reaper part of our program. Then we're back to the conditional compilation translation layer, where merger merges all these versions of the software together into one configurable version. We do not do it by unification, because that's very costly. Instead, we had the Cedar also put placeholder seeds for conditional ranges that are not enabled, that are not activated in these different versions of software. For example, the left version could have been processed with feature 1 enabled, and the right version was processed with feature 2 enabled. So by also putting these placeholder tags, our merger will be able to pair these flags and kind of like git merge, select the right version to put into the merge software, and at the same time, of course, put feature tags to it. Yep. So overall, Hayroll preserves abstraction and configurability in transpilation. Evaluation. We ran Hayroll on libmcs, zlib, and crustbench. On correctness, Hayroll passes all the tests that cd-rust was able to pass. On translator performance, we run at 500 lines of code per second approximately, which is 20 times slower than cd-rust, but this is a one-time effort. It's much faster than LMs. And with regards to coverage, this is a fraction of macros we're able to translate. So overall, we were able to translate over 50% of the macros in these three libraries, And there's a huge difference between different libraries because people use macros in very different styles. For example, in libmcs, this is a math function library, and they have very disciplined use of macros, basically math functions. So we're able to translate almost all of them. And in zlib and crustbench, there's a lot more non-syntactical use of macros, which we were not able to translate in a best way. We just left them expanded. But this doesn't mean we cannot translate their program. It's just that the macros are left expanded. Performance. Mackie, the macro analyzer, is taking up the most time because for each of these macro translation layer runs, it has to be invoked independently. And the Pioneer part, our symbolic executor part, took the number 2 most time. It has only to be run once per translation, but for programs with more configurability, it runs significantly slower. Yeah, so that is Hayroll. We translate C macros into Rust functions or macros, and we translate C conditional compilation into Rust CFG attributes. We open sourced Hayroll, and the C Rust team is working on integrating Hayroll. You're welcome to fork us.
All right, thanks for the talk. We're ready for some questions.
Hi, thanks for the talk. I was wondering, so how do you ensure that the behavior of things like feature 1 and feature 2 are actually disjoint and not like influencing each other? Because there's sometimes, is that part of the symbolic executors?
Yes, that's part of symbolic executor.
And then the second question is, how do you keep all the garbage macros from being included in like a bunch of things that like maybe libc sets?
What do you mean by garbage macros?
Like,
do you mean the ones that are never used?
No, there's a bunch that are just like underscore libc and then like, or sorry, glibc, and then like they set things to tell you kind of like version gate the different library versions and stuff.
Yeah, so we had a flag that says like, what is the project, what is the boundary of your project? Okay, what is the macros that you care about? So all the system ones or the ones that you don't define as developer in your project directory, we don't care about that.
Okay, so it's only the ones that you include.
Yeah. Okay. So basically we're doing concrete execution combined with symbolic execution, and the part like the library one are concretely executed.
Hi. My experience, most open source projects will have lots of macros, and there'll be some configurations of the macros that where the system simply doesn't build. Maybe it has junk code inside an if-def or something. How do you handle those? So we have a whitelist mode, which also allows you to tell the symbolic executor which flags you care about, you want to explore. If you don't tell it anything about a whitelist, it's just going to explore everything. Well, I think what I'm saying is that sometimes there'll be like combinations of 2 or more macros where if macro foo and bar are both defined, then we don't know what's going to happen then. I see. Yeah, a best practice for having this kind of macros in the C code is by writing if def A and B, then hash error. I know not everybody does that. Yeah. So this is something you need to tell our symbolic executor for us to know. Otherwise, nobody will know. Thank you.
I enjoyed the talk.
Thank you.
I understand Rust's proc macros are unhygienic. Do you have any plans to use that to tackle unhygienic macros from C land?
Sorry, what macros in Rust are unhygienic?
Proc macros.
I don't really know that. But
okay.
if we know there's something we can do, but definitely we will.
Okay.
They're not really unhygienic, but not it's complicated.
So I'm curious about the merger phase. Different compilation options could cause the common code to translate differently to Rust, right? So what happens when the merger encounters common code that didn't actually get translated the same from C to Rust?
Sorry, can you repeat your question?
So like in this example, you have like separate code and then there's some common code with regardless of feature. If the C to Rust translator translates them differently, what happens in that case?
Well, we made it an assumption that for the common code part, the C to Rust translator is going to translate them into the same thing. But if they don't, we will issue a warning.
Okay, great. Thank you. All right. Thanks for the Q&A. Let's thank our speaker again.